Welcome to Pre-Calculus. Let's continue investigating function symmetry. We've looked at two examples. One was an even function, one was an odd function. Let's see two more examples where we have to, again, make a conjecture looking at a graph and then proving whether it's even, odd, or no symmetry whatsoever. Here's our first of these last two examples. So we're looking at the function f of x equals base e to the power of x. So let's begin by graphing this function, and we'll do that by creating a table of values, table of coordinate points. We'll put our x values there in the left column and our f of x or our y values there in the right column. So we'll choose our traditional -2 through +2. But I do want to also include this number e. In fact, we'll see e in all of these. So I'm going to go -2 through +2. And let's work on evaluating this function. So I'm going to put in f at -2. So again, we're just substituting that x value with the number -2. So this is going to be base e to the power of -2. Now I can deal with the negative exponent. Remember, the negative exponent gives me the reciprocal or the flip of the base. So if I think that e is e over 1, this is equivalent to 1 over e to the power of +2. But then I'm really not knowing how to proceed in terms of simplifying that expression. I don't know what to do with that e. Well, e has a value of about 2.72. So it's an irrational number. And even knowing that, it's really difficult for me to square 1 over 2.72. So at this point, I really want to think about what other tools I've got in my tool belt in order to evaluate numbers. And I think a good option is to use the graphing calculator. So I'm going to head over to Desmos. And I'm going to type in that function f of x equals e to the power of x. So we've got a graph there, and let's get a table of values so that we can create a graph on our notes screen. So I'm going to click Edit List, the little gear there, and then I'm going to convert it to a table. And we can see that those numbers are really irrational. So -2, the one we were just trying to evaluate, has a rough value of 0.1 about 4. I'll record the others. So at -1, it has a value of 0.37. 0 has the value of 1. 1 has the value of about 2.72, and that's the value of e. And then 2e squared is about 7.39. So I've recorded those. I've got what I need from Desmos. I'm going to head back to our notes screen so that we can complete our table. So f at -1 is, again, I'm taking this from Desmos, so I should back up. This is about. F at -1 is about 0.37. I'll back up to evaluate e to the power of -2. That's 0.14. Now, f at 0 we saw was just 1. We should ask, why is that just 1 when all these other numbers are so many decimals? Well, if I use the function, it's e to the power of 0, and that shows us right away anything raised to the power of 0 is 1. So that's why we're getting a nice point there. F at 1 is the value of e itself. Anything to the first power is itself, so that's about 2.72. We had seen that already. And then our last value, f at 2, has the value, this is about e squared, is 7.239. Well, we'll pull those points over to write them as coordinate pairs. So we got -2, 0.14. -1 is 0.37. 0 is the nice even 1, really it's an odd number, but it's a clean number. Sorry, not 0, but 1 is 2.72. Again, that's the value of E itself. And then 2 is 7.39. So I'm going to sketch those points here. I'll plot those points. We'll sketch the graph. So at -2, we're almost at the x-axis. -1's not much higher up. It's still in the positive y direction. So that's all in quadrant 2 there. 0's at 1. 1's at 2.72. That's on the wrong side of 3. There's 2.72 about. And then 2 has the value of 7.39. So I've got my framework in place. Now, one thing I noticed from the graph we had seen on Desmos is that there is a horizontal asymptote here on the x-axis. So if we think of what kind of function this e to the power of x is, this is one of our exponential functions. So definitely an exponential function will always have a horizontal asymptote. This one's at the x-axis, so the line y equals 0. And that tells me that none of these points pass down into the lower part of the graph. There's no part of this function that exists in quadrants 3 and 4. So we've got this exponential curve. And there's our first task. We've graphed that function. Now we want to make a claim for the exponential base e function in terms of its symmetry. Do I think that that's an even symmetry, an odd symmetry, or neither? So again, I'm going to compare that with my the graphs that I had to see, can I get this graph back to itself if I were to fold it across the y-axis? Now I can just look at the graph itself. If I were to reflect this graph over the y-axis, it would look something like that in the red. So although that does kind of show a reflection, the graph does not land on itself. Now that makes me think, no, that's not an even function. Remember, an even function is one I can fold over the y-axis, reflect it over there, and it should hit itself. So I'm going to back up from that hypothesis. Well, let's think the other possibility is that if I rotated it 180 degrees around the origin, will the function at that point get back to itself? Well, that would give us some function roughly like this. And although that's an interesting rotation, the green graph doesn't come back to itself when I do that rotation. So my feeling is that this graph doesn't show even symmetry or odd symmetry. So my initial feeling is no symmetry. Well, let's check it with our algebra. So we had two rules here. For even symmetry, it's f at -x equals f at x. And then for odd symmetry, we had the second rule, f at -x equals -f at x. So notice part of those rules is the same. It always starts with f at -x. So let's just calculate, see what we get, and see if the result supports our hypothesis that this exponential base e function shows no symmetry. So I'm going to take the function, it's e to the power of x, and I'm just going to plug in -x. So e to the power of -x is e, I'm sorry, let me back up. So remember that negative power just gives me the reciprocal. So it's really going to look like what we saw here in our table. It's going to be 1 over e to the power of positive x. I'm getting ahead of myself. 1 over e, that whole fraction to the power of x. So that's what f at -x equals. So we can ask ourselves, if we're thinking about even, does that have the value of the original f at x? Does this equal e to the power of x? And definitely not. Those are not equivalent. So it's not even. So I can say therefore not even. Let's check for the other option, the odd option. So that one says if I've got f at negative x, does it equal negative f at x? So I've already found f at negative x. That's this 1 over e to the power of x. Let's calculate what's negative f at x. That one's pretty easy. You just take the f at x, which is our original e to the power of x, and you put a negative out front. Well, again, that does not equal what we found here in the blue, 1 over e to the power of x. Those are not equivalent graphs. Therefore, it's not odd. And that statement there would be our proof to say that this does not show even symmetry or odd symmetry. And that supports what we had seen graphically, considering folding over the y-axis or rotating 180 degrees around the origin. All right, let's wrap up our discussion of function symmetry with one final example. So our fourth function here. Again, I want to graph it. So I've got this function f of x equals the absolute value of x. Do you remember the absolute value of x? So we'll put f of x here in our right column. X is there in the left. We'll name this one, it's absolute value. And we'll use -2 through +2 for our domain values. And let's evaluate. So we're going to choose f at -2 first. And let me get our red ink for this, f at -2. So I'm going to take the function absolute value of -2. And we got to remember what absolute value does as a function. Really what it's saying is, how far is this x value from 0? So if I think on a number line, here's 0, -1 and -2. How far is -2 from 0? It's 1, 2. So it would have the output of 2. We'll use that same idea when we calculate f at -1. So again, if I place the -1 for x in the function, that's absolute value of -1. And just like we calculated for -2, how far is -1 from 0? It's 1 away. So it's a distance function. And the bottom line is it makes anything negative positive because distance is always positive. I never say, hey, I live -2 miles away from the school. You would always say some positive number. Let's calculate f at 0. So a little bit of a tricky statement here. How far away is 0 from 0? Correct. It's 0 away. Okay, f at 1. With the positive numbers, it's a little easier. We're really used to positive numbers. So 1 is 1 away from 0. So it has the output of 1. And then f at 2 is absolute value of 2. 2 is 2 away from 0. So I am seeing this telltale symmetry where the numbers are identical and the signs are the same as well. Let's graph this function. So we've got the points -2, 2, -1, 1, the origin 1, 1, and 2, 2. So I'm going to plot those points. And what we'll see is that the absolute value function has this very characteristic V shape. So on the left, the whole graph's here in quadrant 2. On the right, the whole graph's in quadrant 1. And that is our absolute value function. So we've done the first task, we've graphed the function. And now we want to make a claim. Does that graph show even symmetry? Can I reflect this graph over the y-axis, and would it hit itself? So let's take this right-hand piece, and I'm going to reflect it over. As I reflect it, it's going to hit exactly on that left-hand side, the part that it's in quadrant 2. So that type symmetry, definitely it's reflectional across the y-axis. So my initial hypothesis is that this is an even function. I can check the odd part. If I were to rotate this function 180 about the origin, the graph would go here. So an interesting rotation, but everything would be down in quadrants 3 and 4. It wouldn't return us to the original function. So that kind of discounts the possibility that it's odd function. Let's pick up our even rule. So the even rule again is f at negative x equals the original f at x. So let's begin by calculating algebraically what's f at negative x. So I'm going to pick up the rule, it's absolute value of x, and I'm going to substitute x with negative x. And I need to use the idea that we saw in our table, how far away is a negative number from 0? And basically what we saw is that it takes that number and makes it positive. So this would become simply absolute value of x. The negative really becomes resolved within the absolute value. Well, let's check and see, does that match the original function? So the original function f of x, and again, I'm taking that from the right-hand side of the rule, is simply absolute value of x. And again, now I'm comparing, how did f at negative x compare with absolute value of x? They are equal. Because those are equal, we can make this statement, f at negative x equals the original f at x. Therefore, again, those 3 dots mean therefore it is even. And that in the box is our answer in terms of an algebraic proof to show that the absolute value function is an even function. Thank you for joining for this investigation of function symmetry. We looked at 4 examples, 2 that were power functions, x to the power of 6, which was even, x to the power of 3, which was odd. And in this section, we saw e to the power of x, which was neither. Exponential function isn't even, isn't odd. And then to end up the absolute value function, which is another even symmetry function. Again, thank you for joining. See you next time.